Now, I've got a piece of glass. So this is something that we use for windows, and we can see through it. I can see you through the glass. So let's see how the infrared does with this piece of glass. Okay, so you see something which is a reflection of Ben. You see Ben in reflection, but you can't see me. The infrared light is not going through the glass. And actually, that's how greenhouses work. They let the light in, but they let the light in, but they trap the heat. Okay, let's see what other things. Let's see if infrared can see through other things. So here's a piece of paper. The rest of the things I'm going to show are things you can't see through with visible light. Now here's a piece of paper, and we can't see through this piece of paper. You can see the left imprints of my fingers where I've warmed it up, but you can't see through the piece of paper. Here is a piece of cardboard. Well, if we can't see through paper, it's unlikely we're going to be able to see through cardboard. Can't see through cardboard. We're going to try out foam. Can't see through foam. Actually, this kind of makes sense. Foam is what we use in coolers to insulate them, to keep the heat in, so it doesn't let the heat through. And finally, here is a piece of gauze, a gauze bandage, and can't see through that either. So those are, whoops, okay. So those are a few things that there's some experiments that we'll come back to when we go to the terahertz frequencies. Okay, thanks for turning off the camera. Well, we still have one part of the electromagnetic spectrum that we haven't filled in, and this is called the terahertz gap. The reason it's called the terahertz gap is that we don't have very good technology to see in the terahertz gap. For example, no matter how much money you gave me, I couldn't go out and buy a camera that would be able to see you at terahertz frequencies. In fact, that part of the subject of the conference that we had here, some of the members of the conference are in the audience. They came from all over the world. We're to talk about science in the terahertz gap, and the technology has actually come a long way, and we're starting to be able to do a lot of things. So this is the heart of the electromagnetic spectrum, and we love it, and that's why there's a heart there. Now, we happen to have at UCSB one of the brightest sources of tunable terahertz radiation on the planet, which is what Dr. Witherell was telling you about, the UCSB free electron laser. I couldn't bring it to the lecture hall because it takes up this building, but I can show you some pictures of it. This is Jing Xu, a former graduate student, now postdoctoral researcher, and she is showing off the UCSB free electron lasers, which are tunable from 0.1 to 5 terahertz. And this is a picture that shows you some more details of the guts of the machine. Now, fortunately, terahertz technology has advanced to the point where we actually are able to, I was able just a few years ago to buy a source of terahertz radiation that I can bring into the room. And it's on the table right here. It's shown up close on the video screen. This is made by a company that was exhibiting at our conference, a company called Virginia Diodes Incorporated. It's really quite a remarkable piece of technology. It's about the size of a shoebox, and it's got a frequency synthesizer that generates microwaves that are tunable from 13 to 15 gigahertz. And then what it does is it multiplies it by 3, and then by 2, and then by 3, and then by 2, and then by 2. Well, when you multiply all those things together, you get 72. So it takes this frequency, multiplies it by 72, and brings it all the way up to 1 terahertz. It puts out about a few microwatts, which is a million times less bright than the maximum power of the free electron laser, but I could bring it into the lab. I could bring it in to show it to you. So if you look at the table, right next to this terahertz source, so the terahertz is going to come out of the front. It's going to come out where that little arrow saying terahertz is, which is right up here. So you can see my finger. The terahertz is going to come out of here. And it's going to go here. And this is a detector. It's a very sensitive detector that's cooled to just a few degrees above absolute zero. So we have this fantastic big display here that shows you a measure of how much power is going through this. So what we're doing is we're converting the power to a voltage, and so that voltage is a measure. If that number gets, well, that number isn't going to get bigger when we put something in between it. Then we'd really have a breakthrough on our hands if we amplified it. So that number is going to get smaller when we put things in between. So we're going to go through and we're going to check these different materials that I just checked with the infrared. So Ben, please, so everybody watch that display. Ben's going to put in a piece of glass. And let's see how much we get through the glass. What do you see?
The terahertz the glass is making?
Okay, so the glass is not transparent to terahertz radiation. All right, now paper we couldn't see through with either visible or infrared, so let's try terahertz. So the numbers went down a little bit, but they're still pretty big and easily detectable. So terahertz radiation can see through paper. All right, now we're going to push our luck, and let's try cardboard. Okay, so go ahead and put in the cardboard. So the numbers are going down by quite a bit, but still, that's an easily detectable amount of terahertz radiation. So terahertz can go through cardboard. Okay, let's try the foam. That's a big, thick piece of foam, but actually it's much more transparent than the cardboard was. So the terahertz is doing pretty darn well. So finally, Ben is going to put a bandage up there, and let's see how terahertz goes with a bandage. Oh, it's doing fine at getting through a bandage. And your clothes. Thank you, Dan. So what I have to say about this is terahertz rocks, right? You can see through all these things that you can't see through with visible light or with infrared light. Well, that's one of the main reasons why we have, one of the reasons that people are interested and one of the reasons behind a lot of emerging applications of terahertz radiation. So I'm going to tell you about a few of these emerging applications that are actually being done at the level of companies, and then I'm going to tell you about some of the research that we're doing on campus. So I told you that we have no cameras for terahertz radiation, so how do you take a picture? I'm going to show you some pictures, nevertheless, that were taken. Well, it's a very painstaking process. So this is an apparatus made by a company called Picometrics, which is sending out a terahertz wave and then measuring the reflected wave from a single point on this painting, which is actually in the Uffizi Gallery in Italy. And so it takes a picture of one point, it measures one point, and then it moves over a little bit and measures another point. And then it moves over a bit and measures another point, and so on, and so on, and so on. So that is one way to build up an image. Now, of course, it takes a long time, so you really have to want to know what there is in order to build up that image. And actually, this is a different painting, but this is an image of the painting as you would see it. This is just a picture. And now zooming in on this figure, this is what it looks like at visible frequencies. And this is what it looks like at terahertz frequencies. To me, that looks quite different. And what's going on here is that painters, and I know there's at least one painter in the audience, painters do a lot of drawing and even sometimes painting underneath the final coat of paint. And so the terahertz radiation can go through the visible paint and see what's behind it. And it looks as though the artist started off with a very different figure, maybe even than we end up seeing. So it's an interesting, very interesting tool for art historians. Completely different application. We all know the sad story of the space shuttle Challenger, and there was a problem with the foam on the external fuel tanks. Well, as we saw, terahertz can go through foam, and actually NASA now uses terahertz radiation to check the integrity of the foam on the external fuel tanks. And if they find a place where the foam, which is applied by hand, if they find a place where it's not quite right, they can see the voids inside the foam, and so then they take it off and redo it.